Good morning. I've learned when you start a lecture in Kenya, you always say good morning. It's really wonderful to be with you all today. My name is Luskin. This is my second day in Kenya and second day lecturing, and it's really truly an honor and a pleasure to be with you all today. We're going to talk today about the topic of information in biology and how is it used and how does it point to intelligent design. So a little outline of what we're going to discuss. We're first going to talk about what is the genetic code. I'm sure that many of you have heard of the genetic code and how it's so fundamental to biology and how living organisms operate. We're going to talk about the genetic code and how it uses information and how that points to intelligent design. We're going to also talk about a concept called junk DNA and how our information in our DNA is performing all kinds of important functions in your body and how our bodies are rich in information. And then finally, we're going to talk about where does all of this code, this information in living organisms come from? How did it get there? And how are our bodies so full of this information? But a little bit of a background on me. I actually did my PhD at the University of Johannesburg in South Africa. So my wife and I lived in Johannesburg for about 4.5 years. This is me at a place called Luskin, which is just north of Pretoria. How many of you have ever been to South Africa before? A few people, great. Yeah, wonderful. So Africa is a continent that is very near and dear to my heart, my wife's heart. We love this continent very much. This is my first time in Kenya, but it's really a blessing and an honor to be here with you. In fact, I've done a lot of tutoring of students in Africa. So this is actually me at the University of Johannesburg Soweto campus on a day when we were teaching high school students there about geology. I was a geology major there. So how many of you have ever studied geology in the past, studied rocks and stones? Okay, well, all right, a couple folks, great. So that's my background, but also I've taken a lot of biology, and one of my favorite topics is biology. So just to kick us off today, I want us to think about sort of a big picture question, and that is, what is the most important question that we can ask in life? Okay, there's so many different questions that we can ask. Maybe we can ask the question, how can I get a good job someday and make money, right? I mean, these are important questions, right? Who does not want to make money someday here? Okay, I didn't see any hands go up. So we all want to get a good job someday and make money. What about this question? When will that special someone finally see what an amazing person I am, right? And think of me. Now, that's also a very important question. We want that special someone to see how amazing we are. But I would say that there's another very important question, a question that all of us have to answer for ourselves, and that is this. Was I designed for a purpose, or am I just here by an accident? Is my life just a random accident, the result of chemicals coming together and making me, and I'm not here for any reason at all? Or was I designed specifically for a purpose? And I'm going to argue that this is the most important question we can ask. Was I designed for a purpose, or am I just here by accident? Now, it's interesting because there are different ways that we can address this question of whether we are here by purpose or by accident. One way we can answer this question is, of course, through religion. We can read the scriptures, we can, pray, and many different religions out there will, of course, address this question. And generally, the answer is, we are here for a purpose. That's usually what a religion will teach you. I personally am a Christian, so I believe that God made us for a purpose. That's why traditional religious belief. But there's another way we can address this question, and that is through science. The scientific evidence is actually capable of addressing this question of whether or not we are here by accident or for a purpose. So today we're going to address this question using science. And we're not going to get into religion, we're going to strictly focus on the scientific evidence and how it points to intelligent design. So our position is that science can help us address the crucial question of whether life in the universe were purposefully designed by an intelligent agent. And we're going to talk about the fact that there is scientific evidence from biology and physics and cosmology which show that life in the universe were intelligently designed. And we're going to also mention that this conclusion has profound implications for science and philosophy that we need to take very seriously. So what does this this idea of intelligent design. I know that idea has been thrown out a lot, and we've been talking about that. This is going to be the theme of the morning today. So, intelligent design is a scientific theory which says that many aspects of life and the universe are best explained by an intelligent cause, because in our experience, intelligence is the cause of their informational properties. And we can say that many features of nature are best explained by an intelligent cause rather than an undirected cause like natural selection. Darwin's theory of natural selection says that everything arose by basically an unguided and blind process of random mutations, chance events that are then acted upon by this blind and unguided process of natural selection. And this is basically what caused everything we see. What we're going to tell you today is that many features of nature are not very well explained by natural selection, but they're actually better explained by an intelligent cause, an intelligent being, a mind, basically a designer that made many features of nature and built into them all kinds of complex, information-rich properties which show that they did not arise by chance, but in fact they were designed by an intelligent being, by a designer. So that's what we're going to talk about today. So let's start with a little biology review today. We're going to talk about the genetic code. How many of you have ever studied biology in school? Yeah, most of you probably have studied at least some biology, so I'm hoping that this will be a little bit of a review for some of you. So a little bit of review, this is your genome. Okay, no, this is not your genome, that's supposed to be a joke. Your genome is the set of all the information that is contained in your cells, okay? So you have chromosomes inside every one of your cells. And your chromosomes are stored in the nucleus of your cells. And in your chromosomes are basically very tightly wound strands of DNA. I'm sure that many of you have heard of DNA before. DNA is the molecule that contains all the information to build all the proteins in your bodies, okay? And proteins are very, very important. Proteins are basically the molecules that make up your body parts and conform most of the important functions in your cells. So without proteins, you couldn't live for even a second. Proteins are basically what make up your bodies and what perform all the important functions in your bodies. And what's interesting is that your DNA is basically this tightly coiled up molecule, coiled up into these chromosomes inside your cells. And along your DNA is information that encodes proteins. And DNA carries information that is written in a biochemical language, and that biochemical language is called the genetic code. Don't worry if some of this is new to you or you're trying to sort it out. We're going to go through a lot of this in more detail as we talk this morning. So in biology, there is something called the central dogma. I'm not talking about a religious dogma or religious doctrine. I'm talking about the central dogma of biology, which is the method by which your bodies convert the information in your DNA into proteins. And the way this works is you start with DNA, and the information in your DNA is then converted into another molecule called RNA, and then that information in RNA is converted into proteins. And then proteins are the physical matter that make up your bodies, okay? So we're going to talk about the central dogma of biology, how your bodies use the information in your DNA to then convert that information into RNA and then into protein, and how all this works, okay? So again, the central dogma of biology is DNA, the information in DNA is converted into RNA, and then RNA is converted into protein, and that's what makes up your body parts. So what is a protein? Well, many of you probably have heard of proteins before. A protein is basically a very long chain of amino acids. Okay? Amino acids are thought of some of the building blocks of living organisms. Do any of you take vitamins? Okay, so vitamins, if you look at the ingredients in your vitamins, vitamins often contain amino acids. Why do they contain amino acids? Because your body needs amino acids to build proteins. And these proteins in your bodies are basically long chains of amino acids, and then these chains, they fold up into very specific shapes to perform important functions inside of your body. So each step involved in making proteins involves a transfer of information. Remember, you're starting with that information in your DNA, then that information in the DNA is then transferred into RNA, and then the information in RNA is then transferred by your cells to create proteins. So each step of this DNA to RNA to protein involves a transfer of information. So here's a question for you all. What exactly is the genetic code? Is it number one, the information in your DNA that specifies the amino acid sequences of proteins? Or is it two, the set of rules used by cells to translate information encoded in your DNA, thank you very much, into proteins? So I don't know if you guys have studied the genetic code, but for those of you who have studied it, who thinks it's number one? It's the information in your DNA that specifies the amino acid sequence of proteins. Who thinks it's number one? Anybody who thinks it's number two? The set of rules that are used by the cells to convert that information in your DNA to proteins. Who thinks it's number two? Okay, well we're being a bit shy this morning, that's okay. So most of the time when I ask people what they think it is, most people say they think it's number one, but it's actually number two. The genetic code is a set of abstract logical rules or a language-based biochemical algorithm that is used by our cells to convert information in DNA into proteins. Okay, so it's literally a set of abstract logical rules that your cells use to convert the information in the DNA into proteins. But I have to ask this question. Where do things like abstract logical rules come from? Do these come about by chance? No, in our experience, things like a set of abstract logical rules or sort of a set of instructions or commands you have to follow, these come from intelligence. Okay, so think of baking a cake. Okay, if you want to follow a recipe is a set of steps or rules that you have to follow in order to bake a cake, right? But that information in the recipe, it doesn't come about by chance. Somebody who's an expert in cooking or baking had to write that recipe and basically strip it out so you would know the steps and the rules that you have to follow. It's a very similar thing that's going on in ourselves. There's a set of steps or abstract logical rules that your bodies and your cells have to follow in order to make proteins. But the thing is, recipes don't come about by chance. Rules don't come about by chance. Rules require a rule giver, or recipes require somebody who's an expert in cooking or baking to make that recipe. So we can see here from the very beginning that these sorts of things don't come about by chance. Some kind of a mind or an intelligent agent had to create these rules so that our cells can follow them. So how does your DNA store information? On the right-hand side here, we see a drawing of the DNA molecule. And your DNA, if you were to take the DNA in one single cell and you were to stretch it out, it would stretch out over 2 meters in length. And it's all coiled up very, very tightly inside the nucleus of your cells. And your DNA is rich in information. And your DNA contains information that is stored in this biochemical language using 4 they're called nucleotide bases. And the names of the nucleotide bases are adenine, cytosine, thymine, and guanine. And we represent them with the letters A, C, T, and G. And so if you think about your DNA molecule, it's sort of this beautiful molecule. It looks almost like a spiral staircase, okay? And in this spiral staircase, it's almost like a ladder. So along the backbone of this DNA molecule, there are rungs of the ladder. And these rungs of the ladder are these nucleotide bases. And along each rung, you have one of the 4 nucleotide bases, either adenine, cytosine, thymine, or guanine. So each one of these rungs is going to be one of these 4 bases, either an A, a C, a T, or a G. Okay, so now what we can do is we can unwind this spiral staircase and kind of lay it out flat and look at what's going on here. Okay, so you can see that if we look at this unwound DNA strand, these would be like the rungs of the ladder here, okay? And so we have 2 different strands of DNA. Remember, there's 2 sides to this spiral staircase. And so there's 2 strands. One of these strands is called the coding strand. And this is the strand that uses the actual information that contains the major information that is used to encode proteins. And you can see that along this coding strand, you have different nucleotide bases. Here's a T, that stands for thymine. Here's another T. Another thymine. Here's a C, that stands for cytosine. Another T. And then here we have a G, which stands for guanine, and an A, which stands for adenine. So we can see that along this DNA molecule, there are these nucleotide bases. Now, on the other side of the DNA molecule, there are also nucleotide bases. So you can see that each nucleotide base actually links up with another nucleotide base on the other DNA strand. And in the DNA, there's, again, we have sort of these rules, these chemical rules, that T always binds to A, and G always binds to C. So if you have a T on this strand, you're going to have an A on this strand. So then we have an A, T here, so there's another A. Here we have a C. C always binds to a G. So we have a C here, there will be a G there, a T here, A there. And here we have a G, so G always binds to C. So here we'll have a C on this strand. And then we have an A here, so because A always binds to T, we will have a T here. So this is called the template strand, or the complementary strand. And you can see that there's basically sort of a mirror image of the information on one strand is then copied in a mirror image on the information on the other strand. So this is how your information in DNA is stored, in these 4 nucleotide bases that are stored along the backbone of the DNA molecule. Okay, so what about proteins? Now, proteins are not made of nucleotides, right? Proteins are made of a totally different type of molecule called an amino acid. And so here we have 20 different types of amino acids that are used by the proteins of living organisms. So proteins are long-chain amino acids. So we can ask the question, how do we convert the information using the 4-character language of DNA, the A, T, C's, and G's, into the 20 amino acid characters of proteins? So there's a different set of characters used in each system. So we have to somehow convert this 4-character language in the DNA to a 20-character language in proteins. And this information conversion process is called transcription and translation. It's a 2-step process. And so we start with transcription, and then we go to translation. We're going to explain how this works right now, okay? So again, we're dealing with information in our DNA. So in the process of transcription, we take the information in the DNA and we convert it into another molecule called messenger RNA. Something about the DNA is a very stable molecule, okay? It's very strong, it's very stable, it doesn't break down very easily. But one of the downsides of that is it's not very good at transporting around in the cell, okay? So because of that, information, your DNA tends to stay in a special location of your cells called the nucleus, in the center of your cells. So the DNA is going to stay inside the nucleus of your cells, but if you're going to use the information in the DNA to build proteins, you need some way to basically transport that information outside the nucleus of the cells, where it can be used by molecular machines in your cells to then make the proteins, okay? So the way that we get the information from the inside of your cells, from the DNA, the way that we then take that information and take it to a place where it can be used is by converting it into a more mobile molecule, a molecule that can be transported around your cells. And that molecule is called messenger RNA. And so basically your cells are full of these things called molecular machines. Molecular machines are basically protein-based machines which go around your cells performing all kinds of important functions. And one of the molecular machines you have in your cells is called an RNA polymerase, okay? So what does the RNA polymerase do? It travels along the DNA molecule, it reads the information in the DNA, and then it creates a copy of that information in a new molecule called messenger RNA. So you can see what's going to happen is this RNA polymerase machine is going to go along the DNA, it's going to read the information in the DNA, and as it goes along, it's going to create this messenger RNA molecule that contains a copy of the information in your DNA, which then is going to be carried out to the ribosome. We'll talk about that in just a minute. But before we go on to that, here we have basically 6 nucleotide base pairs here. 1, 2, 3, 4, 5, 6. But the question is, how many nucleotide base pairs are in your DNA in your cells? If you look at all the DNA in all of your chromosomes, how much information is in your chromosomes? Well, here we're just showing you sort of a very representative or schematic example of the information in your DNA. So we only have 6 base pairs here. But if you were to look at all the information in your DNA, there's actually 3.5 billion base pairs inside every single one of your cells in your body, except for red blood cells. They're a special exception. They don't use DNA. But all the rest of your cells in your body have 3.5 billion copies of these nucleotide bases in all of your DNA. That's a huge amount of information in your DNA, you guys. And your cells are constantly, each molecule is kind of like DNA, and then it also uses these nucleotide bases to store information. But instead of being that double-stranded molecule, remember DNA was that spiral staircase with the 2 strands? Well, RNA has only 1 strand, but it still uses these nucleotide bases, okay? So within a typical structure of an mRNA molecule, there are different sections of information, and each section has an important function. So we start with this first part called the 5' cap. And this is the part that basically protects the RNA molecule from being degraded or destroyed in the cell. Then we have another section called the 5' untranslated region. This section helps our bodies understand how to convert the information in the RNA molecule into proteins. Then we have the most important part of the mRNA molecule, which is called the coding region. We're going to talk more about this in just a minute. This is the section that carries a copy of the information in your DNA out to this other molecular machine called the ribosome, where it's then converted into proteins. We then have a couple other sections called the 3' untranslated region on the poly A tail, which also help with your cells to properly process the information in the RNA. Okay? So after your body converts the information in DNA into RNA, then that RNA molecule is taken outside of the cells to another molecular machine called the ribosome. And the ribosome is a very important molecular machine because this is where your proteins are actually made. This is a molecular machine that actually makes the proteins in your bodies. And what this ribosome does is it reads the information in your DNA, reads the information in the RNA molecule and directly turns it into a protein. So this step of information conversion is done using the genetic code, the abstract logical rules mentioned earlier. Let's talk a little bit about how this works. So if you look at, let's think back here, we have on the right-hand side here, we have a DNA molecule. And on the left-hand side here, we have an mRNA molecule, okay? And the way that your DNA stores information is in a set of 3 nucleotide bases called a codon, okay? So a codon is basically 3 nucleotide bases. Here we have the nucleotides A, and G, okay? And so remember, A always goes to T, A always goes to T, and G always goes to C. So when your body takes the information in the DNA and copies it into RNA, it's making a copy of this information here. So what we're going to see on the RNA molecule is a copy of this information. So remember, A always goes to T, but one little catch. In RNA does not use T. It uses a different molecule. Instead of thymine, it uses a nucleotide base called uracil, which we represent with the letter U here. So in the RNA, instead of A going to T, A always converts into a U. Okay, so as your cells read the information in the DNA and convert it into the RNA molecule, you can see here on the RNA molecule, we have a codon. And this codon here is going to be U, U, and C. The A goes to U, the A goes to U, and the G goes to C. Okay? So we converted the information in one codon in the DNA into a codon in the RNA. And so then now we'll do a second codon. Again, the A goes to U, the C goes to a G, and the T goes to an A. So we're converting the information in the DNA into RNA, okay? So now what are we going to do with the information in the RNA? Well, now we're going to use the genetic code to actually convert the information in RNA into a protein. And remember, what is the genetic code? The genetic code is a set of abstract logical rules that is used by your cells to convert the information in your DNA into a protein, okay? So how do these logical rules work? I know you may have to kind of squint your eyes to see this, but what we have here on the left-hand side is a codon table. A codon table represents all the possible combinations of the 4 nucleotide bases in your DNA that will actually, we'll call it now in the RNA. So it's going to be U, C, G, and A. These 4 nucleotide bases. And if you have 4 possible nucleotide bases and 3 potential slots in each codon, then there's 4 times 4 times 4 possible combinations, or 64 possible combinations of every set of 3 nucleotide bases. So on this table, there's actually 64 different orderings of the 4 nucleotide bases. So you can see we have UUU, UUC, UUA, UG. You can go through, and every possible combination of 3 sets of letters A, G, U, and C are represented on this table. And what this table shows us is basically what each of those 3 letters of these codons in the genetic code, what each of them possibly represent in the rules of the genetic code. So, for example, let me show you guys how this works. If we have this first codon is UUC, and we want to know, what does UUC stand for in the genetic code? Well, we go over here and we find UUC, and we see that it actually stands for this amino acid, phenylalanine, okay? So phenylalanine is an amino acid that helps to build up the proteins in your bodies. And represented here on the codon table are all of the different 20 amino acids that are in your proteins. And this codon table tells which codon stands for which amino acids, okay? So that's basically what's going on here. We're showing how you're converting the information in the DNA into amino acids. So this first codon is UUC in the genetic code. That tells your bodies to add a phenylalanine amino acid into a protein. But what about this next codon? This next codon is a different command. It actually represents what's called a stop codon. So if you're converting the information in the RNA molecule into a protein in the ribosome, when your body encounters a UGA codon, basically the letters U, G, and A, that tells your body to stop building the protein. It's now time to stop building the protein. The protein is finished, and you can then let it go into the cell where it can perform its function. So again, what we're looking at here with this codon table is basically how we convert the information in DNA into the right amino acids so your body can have the right functioning protein. So just to give you guys a little understanding of how this works, we're going to watch an animation real quick, and I think that hopefully it's not going to be too loud, but we'll start this animation to show you guys how this works.
In 1957, Francis Crick first proposed that chemicals called bases along the spine of the DNA molecule function as alphabetic characters in a written language or digital characters in a machine code. This animation shows how this digital information directs protein synthesis. First, a large protein complex separates the tightly wound strands of DNA to prepare for the copy. During this process of transcription, a protein complex called a polymerase produces a single-stranded copy of the original instructions. Here we see this copy of the messenger RNA molecule being constructed inside the polymerase as individual bases are positioned and added to the growing strand. Now we see the polymerase in action from the outside as it spits out the messenger RNA transcript. Next, this RNA transcript approaches and passes through a molecular machine called the nuclear pore complex. An information recognition device that controls the flow of information in and out of the cell. Now we see the genetic assembly instructions on the messenger RNA approaching and arriving at a two-part chemical factory called a ribosome, the site of protein synthesis. As the messenger RNA transcript passes through the ribosome, the process of translation begins. During translation, the mechanical assembly line builds a specifically sequenced chain of amino acids in accord with the instructions on the transcript. These amino acids are transported from other parts of the cell by molecules called transfer RNAs, which link specific sequences of bases to corresponding amino acids. The sequential arrangement of amino acids determines the type of protein constructed. When the construction of the chain is complete, it is transported to a barrel-shaped machine and helps fold it to the precise shape After the chain is folded into a protein, it is released in the outer cytoplasm to do its job in the cell.
Okay, so you guys can see sort of an illustration of how this process works of converting the information in your DNA to build proteins. But what I want to emphasize for you guys is that this whole process uses the genetic code, where each of those 64 codons represents a specific command or instruction, which is interpreted by the machinery of your cells to create proteins in the proper way. And that genetic code is a set of abstract logical rules. In fact, and this is sort of a big point I want you guys to get, the genetic code represents a language of commands and instructions that resemble computer programming. And those commands and instructions that are in your DNA, they are then interpreted and executed by molecular machines in your cell through a computer-like system of information processing. So it's really quite extraordinary how your cells literally contain computer-like instructions and commands, and then they are read by machines in your cells, much like a computer will read software to execute those commands and give you the proper output. And of course, the proper output is the proteins that your body needs to be able to work. So what am I saying here? What I'm saying is that our DNA literally contains commands and instructions written in a biochemical language that is much like software or computer code. And our cells are processing that information in much the same way that computers process information, okay? So I'm not the only one who says this. How many of you guys use Microsoft Windows computers? Have you guys ever used Microsoft Windows? Yeah. So you may have heard of Bill Gates. Bill Gates is the famous founder of Microsoft. He basically invented the company Microsoft. And Bill Gates, to my knowledge, is not a proponent of intelligent design. Bill Gates actually lives in the Seattle, where I live, the city of Seattle, where I live in the United States. But he says that human DNA is like a computer program, but far, far more advanced than any software ever created. So it's really quite extraordinary that one of the biggest experts in computers says that human DNA is like a computer program, but far, far more advanced than any software ever created. Richard Dawkins was mentioned earlier by your Deputy Vice Chancellor, who noted that he's a very famous critic of intelligent design and a very famous atheist. So he's no friend of intelligent design. But even Richard Dawkins says that the machine code of the genes is uncannily computer-like. He says that apart from differences in jargon, the pages of a molecular biology journal might be interchanged with those of a computer engineering journal. So this is really quite extraordinary. Another leader in the field of biotech named Craig Venter, he says that life is a DNA software system, and there is software in life containing digital information or digital code, and he says that the cell is a biological machine full of protein robots. So leading scientists recognize that our cells are full of information, and even information that is like computer software. Some of you may have heard of Francis Collins, who was the head of the Human Genome Project. He says that DNA is something like a hard drive on your computer containing programming. So, and another paper in the journal Nature, one of the top scientific journals in the world, it says that DNA can accommodate almost any sequence of base pairs, any combination of the bases adenine, cytosine, guanine, and thymine, and has any digital message or information. So there is a code in our DNA, there is a message in our DNA, and there are computer-like commands and instructions in your DNA which resemble computer code, which your cells are interpreting through computer-like information processing to then give you the proper output in your bodies. And for many of us in the intelligent design research community, we think that when we find things like language-based code, computer-like code, commands and instructions, and computer-like information processing and machines, in all of our experience, these things come only from an intelligent mind or a personal agent. So we think that this is good evidence that living organisms and their DNA were designed. But wait, there's more, okay? So we're going to get into some more here, more information in biology. So some of you may have heard of the idea of a palindrome. Well, what is a palindrome? A palindrome is a word that has the same spelling both forwards and backwards, okay? So an example would be the word race car. If you take the word race car and you spell it backwards, it spells the same thing. Or the word tenant or kayak, they both spell the same things forwards and backwards, okay? So that's what a palindrome is. Well, what is a heteropalindrome? Well, a heteropalindrome is a word that can give one message when you read it forwards, but then a different message when you read it backwards. It's kind of hard to think of examples of these, but I had to go Google this on the internet and I found some good examples. So one example would be the word diaper. If you read it backwards, it says repay. Or the word gateman. If you read it backwards, it's the word name tag. Or the word lamina, which is like a little layer. The word lamina backwards spells the word animal, okay? So these are heteropalindromes. If you read the information one direction, it gives you one meaning. If you read the information backwards in the other direction, it gives you another meaning. So let's try to make a heteropalindromic sentence. A sentence where if you read it forwards, it gives you one meaning, but if you read it backwards, it gives you another meaning, okay? So here is the sentence we're going to try to use. It is highly unlikely to evolve an overlapping gene by chance. Okay, so let's read that sentence backwards. I can't even read it, okay? It's just gibberish, right? It doesn't mean anything. So it's very, very difficult to get a sentence or words or a paragraph where when you take them going in one direction, they give you one meaning, and when you take them in the other direction, they give you a different meaning, okay? So this problem is actually not at all unlike biology. So in biology, we talk about the fact that proteins are very long chains of amino acids, right? Well, it turns out that most sequences of amino acids will not give you a functional protein. They actually won't work, right? So the vast majority of combinations of amino acids will not give you a functional protein. Only very, very rare and very, very special and precise sequences of amino acids will give you a functional protein, okay? So just as the vast majority of random combinations of letters will not give you a meaningful sentence, so the vast majority of DNA sequences will not give you an ordering of amino acids that gives you a functional protein. You'll get an ordering of amino acids, but it won't do anything for you. It won't actually work in your cells. Only very, very rare orderings of amino acids give you a functional protein, okay? So if you think about the genetic code, all right? Remember, there are 64 possible codons. There are 4 nucleotide bases in the DNA. Each codon has 3 nucleotide bases, so you can have 4 at each space in the codon. So 4 times 4 times 4 is there are 64 possible combinations of those letters in your DNA when you take them 3 at a time, all right? And every single one of those 64 codons is used in the genetic code. So for example, UUC gives you phenylalanine, but if you take it backwards, CUU gives you a different amino acid called leucine. So because every single one of the 64 codons in life has meaning, within the genetic code, every codon is a potential heteropalindrome, right? So if you take a codon like CUA, again, that encodes leucine, then you read it backwards. And we go to AUC, that encodes a different protein, different amino acid, which I believe this is isoleucine, okay? So you can take these codons forwards and backwards, and every single codon is a potential heteropalindrome. Read forwards, it will encode one amino acid, but if you look at it backwards in the opposite direction, it will give you a different amino acid within the genetic code here, okay? Now, what's interesting is remember how the DNA has 2 strands, right? There's 2 strands of information. There's the coding strand, and then there was what we call the complement strand, or the anti-set strand. So the question we're going to ask is, can these 2 opposite strands of DNA be transcribed and translated to give us functional proteins? Can you have information basically running on both strands of the DNA? Because remember, there's different information on both strands. If there's an A on one strand, there's going to be a T on the other. If there's a G on one strand, there's going to be a C on the other. So can those 2 different strands of DNA, can they be read to give us useful information to encode functional proteins on each strand? And the answer is yes. Sometimes we do get this, and we call these overlapping genes. Because remember, a gene is a stretch of DNA that encodes a protein. So you can have one gene on one strand giving you one protein, and then a different gene on the other strand giving you a different protein, okay? So what's going on and how does this work, right? So let's say we start with this strand of DNA, all right? And we have these codons here, CAC, CAG, CCA, ACA, AGG, TGC. And this is basically a gene, okay? It's a section of DNA that is encoding a protein. This is useful information inside of your DNA. But remember that DNA is double-stranded. So on the opposite strand, you're going to have a different set of nucleotides. And remember that, again, A always goes to T, and C always goes to G. So as we read this other strand going in the opposite direction, we get a different set of nucleotide bases. Because there's a C here, there's going to be a G here. Because there's an A here, there's going to be a T there, etc. So on this strand, it's going to be GTC, GTC, GGT, TGT, TCC, AGC, okay? So the information is now a different set of codons on this other strand of DNA. And what it turns out is that these codons will encode one set of amino acids here, okay? I want to check my notes. So on the top strand, the amino acids that you're getting from this top strand of DNA is going to be histidine, glutamine, proline, threonine, arginine, and cysteine. Those are the names of the amino acids. But then on the bottom strand, you're going to get a different set of amino acids that are being encoded. And that's valine, glycine, cysteine, serine, and threonine. So you can see in this way, you can get different sort of sequences of amino acids encoded by each strand of the DNA. One strand will give you one set of amino acids, and the other strand can give you a different set of amino acids. And this is what we call an overlapping gene. You have one gene here on one strand of DNA, and another gene here on the other strand of DNA. So I shouldn't say overlapping gene, these are overlapping genes, because there's two of them. You've got a gene on one strand of the DNA and a gene on the other strand of the DNA, and each one gives you a different protein, all right? And this happens in biology. So what we're looking at here is basically heteropalindromic information in DNA, because on this strand you're reading the information in this direction, and on this strand you're reading the information in this direction, and you're getting a different set of codons each direction. So this is heteropalindromic information in DNA. And we would call this information compression. You're finding lots and lots of information that's useful stored in a very, very compact space. And when you have information compression, it's very, very unlikely to get this amount of information stored in such a small space. And this suggests intelligent design, because it's very, very unlikely this would come about by chance. You need some kind of an intelligent agent to encode this information. And researchers have actually shown that the genetic code is optimized to allow these overlapping genes to exist. But wait, there's even more, okay? So in DNA, we have this concept called an open reading frame. An open reading frame is basically a portion of the DNA sequence that is converted to RNA and then it's read 3 nucleotide codons at a time to be translated to proteins. So here, these yellow boxes represent an open reading frame. So we start here with this nucleotide, the CAC, that gives us one codon, then we go to the next codon, CAG, etc., 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 okay? And so this is called an open reading frame, where we start with this nucleotide right here, this C, okay? What we can do in the DNA is we can actually start at the next nucleotide, and that gives us a different open reading frame, which gives us a different set of codons, which encode a different set of amino acids. So what we're going to do is we're going to shift over by one nucleotide here, okay? So we just shifted over by one nucleotide. Now we're going to start reading our codons here. So instead of CAC, now we have ACC, AGC, CAA, CAA, GGT, and so on. So this gives us a different set of amino acids according to the genetic code. And same thing on the other strand of DNA. It gives us a different set of amino acids according to the genetic code. So what we're looking at here basically is information that is encoded on the DNA. Again, we have information on both strands, but by starting at the next nucleotide over, we can get a totally different set of codons, which encode a different set of amino acids, which can give us 2 new proteins, one on this strand of DNA and another on this strand of DNA. So instead of 2 overlapping genes, now we can have up to 4 overlapping genes. within the DNA, there's actually 3 potential open reading frames. So we saw one. Now we started here first with this first open reading frame, starting with this C. Now we're starting with this A, and that's the second open reading frame. And now, if we start reading the DNA at this C here, we can get a third open reading frame that will give us a totally new set of codons here. Okay, so if we just shift it over, we're starting now with a new set of codons here. And this encodes a new set of amino acids. We have CCA, GCC, AAC, AAG, GTG, and this gives us a totally new set of codons and a new set of amino acids that are encoded on both strands of the DNA. So what's going on here is we can actually have, along any stretch of DNA, we have the potential to code for up to 6 open reading frames. That's 3 open reading frames on each strand, encoding up to 6 different proteins. This is a huge amount of information compression, carrying capacity, and potential information compression, okay? So, just to give you guys an idea of how it works, we have gene 1 here, which would be encoding a gene along this stretch of the DNA. We have another gene along the bottom strand of the DNA, and then we have another gene here on this top strand of DNA. So we can have, this is just showing you how we can have 3 genes encoding 3 different proteins that are overlapping with each other along any stretch of DNA. So the largest number of overlapping genes that I'm aware of along any stretch of DNA that's been discovered so far is actually 3. But this is still incredible information compression, and there are probably many more overlapping genes that are waiting to be discovered. So when we see all this information compressed into one place, this shows us, again, that there is intelligent design going on in life. To put all this information in the DNA is not going to happen by chance. You need a mind to be able to come up with all this information and put it into the DNA. So what I'm going to do is I'm going to skip this next part because I want to actually show you guys a video at the end, and I think that that's what will explain what's going on much better here. So give me just a moment here, and we're going to talk about where does all this information come from. Okay? So, what is the origin of all the information in the genetic code? All right? Let's ask this question: where does all this information come from? Well, Stephen Meyer is actually our boss at Discovery Institute, and he has said that our experience-based knowledge of information flow confirms that systems with large amounts of specified complexity, especially codes and languages, invariably originate from an intelligent source, from a mind or a personal agent. So what is he saying here? What is at the heart of life? What we see at the heart of life is a language-based code. And what Dr. Meyer is saying here is that in all of our experience, when we find a language-based code, it always comes from intelligence. But yet, again, what do we see at the heart of life? We see a language-based code, including codes within codes, layered in our genes throughout all of our DNA, on top of and controlling the DNA. So codes are everywhere in biology, but ultimately, in all of our experience, codes arise from intelligence. So I would say that the language-based codes and the encoded information that we see in biology always comes from one known source, and that would be intelligence. Moreover, unguided evolution, random mutation, struggles to explain the mass functionality in our genome and the highly compressed information in the form of overlapping genes. And an important point I want you guys to take from this is that all this information that's basically running the show in biology is immaterial. It's not actually a material thing. It's not made of matter or energy. Information is something distinct and different from matter and energy. But life is fundamentally based upon information. What do I mean when I say that information is immaterial and distinct from matter and energy? Well, I could take information. I could write, the 10 Commandments on a tablet of stone, right? But I can take that same information and I can transfer it to a piece of paper. Or I can use an airplane to write it in the sky. Or I can write it on a computer using Microsoft Word or something like that. Or I can store it on a thumb drive. Or I can even write that information in DNA. So information, you can have the same information and you can store it on different forms of matter. So the information is distinct from the matter that is storing it. Information is something that is immaterial. And yet, information is at the very heart of life. So if life is fundamentally based on information, then life is fundamentally based upon something that is not material. This challenges materialism, and it challenges atheism, and it challenges the idea that all that exists is matter and energy, because our bodies are fundamentally built upon information, and information is not something that is made of matter. So if materialism were true, if it were true that all that existed was matter and energy, you could not exist, because you exist because there is information in your cells. So we finished a little bit early, so I have time to show about a 10-minute video really quick. Is that okay, you guys? And I think this will explain things very nicely for you, and we'll finish this up. So, okay.
Think about some of the coolest design things. Cell phones, rocket ships.
So really quick, this is actually a video that is premiering on Discovery Institute's YouTube channel this week. So if you don't catch it all right here, you can catch it all on our YouTube channel. And this is talking about exactly what we talked about today, the information in biology.
Think about some of the coolest design things. Cell phones, rocket ships. When we look at them, we find layer upon layer of complexity. Things specifically...
Sorry guys, hold on. I don't know why it's not playing there. Let me move it to the other screen. There we go. Okay, sorry, I didn't realize that. Okay, there we go.
Think about some of the coolest design things. Cell phones, rocket ships. When we look at them, we find layer upon layer of complexity. Things specifically designed to carry out tasks, millions of lines of code or engineering in order to do what they do. The more we understand about how these apps or spaceships work, the more impressed we can be at the sheer amount of information needed to create all these parts and get them working together to perform a function. Even if we had never seen a rocket ship before, we would know that it was designed by someone. As complex as all of these things are, they pale in comparison to this.
The single-cell bacterium.
And that pales in comparison to your handsome or beautiful self. Look at you, so amazing. Why are you and this little bacterium so amazing? Glad you asked. Running your cell phone and these spaceships are thousands of lines of code, as well as the hardware that makes them do their thing. Inside of you, and this little bacterium, is the same thing, but more advanced. There is a digital code being interpreted or read by computer-like information processing hardware happening inside of you. A world of factories upon factories, building micromolecular machines that cause your hair to grow, make blood, muscles, energy production, waste disposal, manufacturing new miniature robots, programmed to make you do the things that let you live. A tiny little metropolis, and what's running all of it is information. But what is information? The reduction of uncertainty. That's not super helpful, I get it. Imagine you had a dog that was asleep. Oh, what a good boy. But he's sick. You don't know what he might want. You're uncertain. He's not providing much information. But if he woke up and started barking at the door, maybe he wants to go outside. Maybe it's the UPS guy. He's eliminating some uncertainty. But if he stood up and said, "It is Tuesday, I would like to eat some tacos," that'd be a lot of information. Language is very good at communicating information. Another way to think about it is this. Information is a message or instructions with meaning. Inside of you is just such a language, and heaps of information, not just in your brain, but in every cell of your body. Each cell has a gooey core called the nucleus. Inside the nucleus are chromosomes, tiny little spools that hold wound up pieces of your DNA. Inside your DNA is your genome, which contains your genes, segments of DNA. Those contain the information needed to make proteins, the machinery of life. Really important, by the way. DNA contains coded instructions and programmed commands that are read, interpreted, and carried out automatically by the cellular machinery in your body, just like computer code. With software, the instructions come in the form of letters and punctuation that are arranged to encode computer commands. In DNA, the instructions come in the form of the nucleotide bases, A, T, C, and G. that are arranged to encode biological commands, amino acids and other instructions as well. There are program instructions in DNA just like in computer code and software. Some of the world's smartest, most eggiest of eggheads agree that DNA is like a computer program, but far, far more advanced than any software ever created. The machine code of the genes is uncannily computer-like. DNA is something like the hard drive on your computer, containing programming. Life is a DNA software system containing digital information or digital code. From Bill Gates to Richard Dawkins, Francis Collins, and Craig Venter, they all agree DNA is a code. This is absolutely amazing because we know that digital computer code and software systems don't write themselves. Advanced programmed technology only comes from one source: intelligence. Of course, some people claim that the DNA code is an exception. They say it could have developed without intelligence. Random mutations or errors could somehow add up over time and create the software code that runs life. Well, think about any software you know. Is a random change going to improve things? Or will it tend to break things? If you change computer code, sometimes even the slightest change, it'll break things. Change DNA and, sorry to say it, you don't get superpowers. You'll get cancers or other horrific diseases or even death. Random changes are about as likely to produce functional software code or DNA code as random typing will make an intelligible novel or paragraph or even a single sentence. Mutations and errors break DNA. Fortunately for us, our DNA code is more advanced than regular old computer code. It has special features designed right into it to automatically minimize potentially dangerous mutations. Remember, the DNA code works because of how the nucleotide bases are ordered. How they're arranged determines the things that they make. And they're read by cellular machinery, not one at a time, but 3 at a time, in a group called a codon. Some codons were built with the 20 different amino acids, which are the building blocks of proteins. Other codons act as signals to start or stop the process of reading a gene. It's a very finely tuned process with multiple redundant safeguards, because one amino acid can be coded by multiple different similar codons. This brilliantly minimizes the detrimental effects of mutations on the DNA code. Sort of like how some words still mean the same thing even if a single letter is different, like color, or gray, or advisor. Basically, the British spell words wrong all the time, but we still know what they mean, usually. In English, only a few words are like this, but with DNA, it's like this for every combination of letters. In other words, the genetic code is specifically set up to minimize the effects of mutations. Like one of those toys you can't knock over, the genetic code is designed to be quite hard to keep down. Here's how it works. Say you need some of the amino acid building block, leucine. Your DNA could code for that with a codon CTA. But what if a little error snuck in? A little rogue particle knocked your DNA around, changing it to CTT? Oh no, surely now you're gonna... Oh no, that still makes leucine. You're totally fine. Well, what if another radioactive particle came and smacked your DNA around some more and changed it to CTC, or CTG, or even TTG? No worries, bud. Like I said, your DNA is exquisitely designed to resist mutations that change the amino acid. Even mutating TTG further to TTA would still make leucine. Your body would still be happily humming along, subscribing to this YouTube channel, liking this video, even with all that nonsense happening inside. Information and code are running the show in biology. Your body is amazing. But would you believe it if I told you it gets even more amazing than that? Good. Good. Because it does. We're only scratching the surface of how impressive, how packed with information your genetic code is. For each codon, set in 3 letters, there isn't just one way for it to be decoded. There are 6 possible ways. And organisms like viruses and even bacteria can make use of all 6 open reading frames. The genes actually overlap one another, not only incredible amounts of information, but information compression. This doesn't happen by chance. Maybe you've heard of palindromes, words that have the same spelling forward and backward, like race car, tenant, kayak. It's a neat trick, but not quite information compression. You're not packing more information into the same amount of space, it's just redundant information. But what if you had words that spell one thing forward and a different thing backwards? A heteropalindrome. That would be special. These words do exist, and they are very rare. It's even more rare to have an intelligible sentence using heteropalindromes. Let's try to make one. It is highly unlikely to evolve an overlapping gene by chance. You end up with gibberish. This problem is actually quite similar to biology. Just as the vast majority of random combinations of letters will not give you a meaningful sentence, and even fewer will give you a working sentence forward and backwards, when trying to build something in biology, like a typical enzyme, the vast majority of possible combinations of DNA letters won't work, even reading them forward. If you had the additional requirement of needing to be read not just backwards, but multiple different ways, well, let's just say the odds don't get any better. This heteropalindromic information in DNA is an astonishing form of information compression that strongly suggests intelligent design. Researchers have shown that the genetic code doesn't just allow this kind of information compression, but it's actually optimized to allow overlapping genes to exist. We have a universe of language, digital code inside of our bodies that is read and processed through complex nanomachines. These work together in a beautiful choreography of mind-boggling complexity to create even more machines. Where in your experience do things like language, proofreading, nanomachines, and information-rich code come from? You know the answer. They have only one known cause: intelligence. Books have authors, machines have inventors, code has coders. Therefore, if we want to understand biology, our own bodies, how and why diseases work, if we want to advance science, we need to view it from a standpoint of intelligent design. Scientists who saw DNA as a product of intelligent design predicted many of these things, new layers of information in our DNA, particularly where other models failed. But more on that in the next video. Thanks for watching.
Thank you guys. One last slide here. If you want to learn more about intelligent design, we actually have an online program for students. You can go to this website, www.discover.org/SEM, and you can apply to attend our online program. So thank you guys very much, and I hope you enjoyed it.